Welcome back. In this sequence, we will explore a bit of the history and motivation behind functional programming. Well, when we are talking about programming, we are in general talking about computing. Computing is the study of the algorithm and the processes that are used to describe and transform information. The basic question when you are doing computing is actually to know how to efficiently automate a process. I mean, this is what is defined actually even in the report on computing as a discipline by the Association for Computing Machinery. Well, the basic components of computing are, of course, a program that describes the transformation of information you want to perform, and a machine that is there to execute the program. It might look surprising, but actually there are really very many different machines available and very different ways of writing a program. Some of these machines and some of these ways of programming were invented well before the first modern computer ever saw the light. So here we will try to recall a bit of their history because, as you will see, this gives us the foundation of functional programming. If one has to pick a date, probably 1928 is an interesting date to choose as a beginning of programming. Why? Because it's a moment where a very famous mathematician, David Hilbert, posed a decision problem. He asked the researcher community to find a way to devise a process to determine whether a logic statement, a logical proposition, is valid or not using a finite number of operations. Well, that was a general statement of the problem, but if you really wanted to solve it, it was needed to be precise and define exactly what is an operation and what is a process of computation. So a lot of people started working on this. One person you probably know very well is Alan Turing. I mean, Alan Turing in 1936 came back with a solution to the problem posed by Hilbert, and he did this by inventing the Turing machine, which is very well known today. I mean, this Turing machine is basically a finite state automaton which is able to read on a possibly infinite tape where you can read and write and then move from one cell to the other on this tape. That's a theoretical foundation of modern computers and imperative programming. Indeed, the tape is a kind of an abstraction of an addressable read-write memory where you can store not only data but also a program. And the automaton is more or less an abstraction of what you can see as a modern microprocessor. Well, in these kind of machines, you write programs that really behave in an imperative way. Indeed, in an imperative problem, what we do is to read, write, and perform general operations and take decisions based on what is present in a memory cell, which is basically our tape, that holds the contents of things you know very well if you come from imperative programming, which are variables. I mean, what are variables? Like C, N, res in this little example you find from a Java excerpt. These are just names for memory cells. I mean, if you look at this problem, indeed, you are computing the factorial function and you spend your time initializing variables, so putting values into memory cells, then reading values on memory cells, performing operation on them, and putting this value back in some other memory cells, and then returning the result. But it's all a manipulation of memory cells. So, well, it's almost the same time, another researcher, Alonzo Church, which, by the way, was Alan Turing's PhD advisor, also solved the problem posed by Hilbert, but in a completely different way. He invented something which is called the lambda calculus. I mean, it really all stays in these two lines here. So basically, his system provided you a couple of symbols, actually 3 symbols, that allows you to write functions without names. I mean, this is read lambda x dot m. This is a function without a name that has a formal parameter x and the body m, also called an abstraction. And then you have what is called an application. You put m next to n, and this means I will call a function m, giving it as parameter the value n. That's an application. Okay, it's very simple. I mean, this is really a theoretical foundation of functional programming. You'd write programs using abstraction and application, basically function and applying function to values, and the only rule which is used to make computation in the system is just this one, which is known as a beta rule, that says if you have a function with formal parameter x and body m, to which I pass as a parameter, actual parameter, a value m, then what I do is just evaluate the body of the function m by replacing the actual parameter n in place of the formal parameter x. And that's the only computational device, nothing else. Well, in functional programming today, we really work basically like this. We define functions, possibly recursive ones, and then apply them to values and compose functions to compute the result we expect. For example, the same factorial algorithm that we have seen before can be written in real OCaml, like this. You see, we are defining a function, factorial, which is recursive, that takes a formal parameter n, check if it is equal to 0. If it is equal to 0, then returns 1. Else, it multiplies its n by the result of computing the factorial over n minus 1. And it's just a recursive definition. Well, in a truly functional programming language, functions are really first-class citizens. This means that you can give a name to them, you can evaluate function, you can pass function as arguments to other functions, you can return a function as a result of a computation, and generally you can use a function everywhere an expression can fit. This is not the case of most of the programming languages you know. And the value of this fact, the function of first-class citizens, will become evident at the end of the course. Well, so we have seen up to now, we have Turing machines, which are the foundation of imperative programming, and lambda calculus, which is a foundation of functional programming. Both of them were born just to answer a mathematical, logical question. But as always, good things come out of something that can be very abstract or far-fetched. Well, abusing the original notation by Church, one could write the second line of the previous program. You see, this line here that says a function that takes an n and provides a result. Using this lambda notation here, you could write lambda n dot something. And that's the reason why today you hear all this excitement about lambdas being introduced in languages like Java and C++. Well, yes, what is happening is that they are just introducing real functions in these languages. Well, we have seen now that Turing machines were the foundations of imperative programming, and lambda calculus were foundations of functional programming. Two very different styles of programming, both born at the origin just to answer a mathematical hard questions posed by David Hilbert in 1928. Well, just after these two solutions, Turing machine and lambda calculus, were introduced in 1936, people started asking whether they were so different from one another in terms of power of computation. And here we have a very nice result by Turing, just 1 year after this introduction of the Turing machine in 1937. He could prove that any function that is computable by a Turing machine is also computed in the lambda calculus, and any function computed in the lambda calculus is also computed by a Turing machine. So in principle, you can program anything in one style or the other style. That was a central result. After that, they started investigating a little more, and they end up with this Church-Turing thesis that says basically that any function that is computed by any computing device is also computed by a Turing machine, so it is also computed using just lambda calculus. In simpler terms, this means is that if you have a general purpose programming language today, well, these general purpose programming languages are all computationally equivalent. There are functions you can program in one, they are the same you can program in another language. So that's not the criteria for choosing one language over the other. Every function can be programmed in a system or the other. But programming languages are really not born equal, despite this, because they have very different expressiveness. Expressiveness is not the same as being able of computing a particular function. It's how concisely, efficiently you can do it. And the quest for more expressive constructs is really never-ending. It has led to different data representation, different execution models, different mechanisms of abstraction. It's a quest that is ongoing today. Yeah. So when you choose a language, you are really looking to something more than just what you can compute with it, but you are looking at other desirable features, like, for example, how safe is a language? How can it prevent you from making mistakes that will appear at execution time? How efficient it is? I mean, can I program a function in such a way that it can be performed more quickly than if I use, as a programming system, another language, for example? How maintainable a code can be? It's not just a matter of writing a piece of code. I must be able to make changes to it, to read it back in an easy way. So depending on the problem you have to solve, I mean, some programming languages may end up being actually much better than others. I think you understand where I'm going. We really believe here that in many cases, functional programming is much better than imperative programming. And actually, this is not just the opinion of the people giving this course today. I mean, if you go back to John Backus, who is the creator of the Fortran language, is one of the first imperative programming languages in the world. I mean, he received the Turing Award in 1978, and during his lecture, which was actually titled "Can Programming Be Liberated from the von Neumann Style?" he said, I want to find a way of writing efficiently functional programs because functional programs deal with structured data and do not require the complex machinery of procedure declaration. I mean, this is an interesting read. We really suggest you to have a look at if you have some time. So already in 1978, John Backus said that functional programming was really interesting to look at. And now, if you look around you, you see that functional programming is really on the rise. I mean, there is a very interesting report on computer science education at Carnegie Mellon where they explain why they are using functional programming in the first year course, because there are some very clear emerging trends in computer industry today. One is that we need for greater software reliability, we need programs with less bugs. We need to be able to prove programs correct. And actually, pure functional programs are really easier to prove correct than imperative ones. On the other side, we also need to harness the power of parallel computation. You know now that there are an incredible amount of computer system clusters, distributed machines available, and you do not just write a program to run a single machine. In general, you want to exploit the power of many, many machines which are available together. And so they say if you carefully choose a set of higher order functions, then it is easier to write programs that can become parallel and so more efficient on multi-core machines or distributed systems than if you do it just imperative style. A very, very well-known example of this is the MapReduce combinator provided by Google. Map and reduce, we'll learn about this in the course a bit more farther away, are just higher order functions. And functions are really all around us because of the expressivity and the power of functional programming is being recognized widely. You see lambda expression introduced in Java 1.8. There are lambda expression introduced in C++ version 11. So the point is, no matter what your preferred programming language is, understanding functional programming principles is really now a basic skill. That's the reason we want to bring you into this journey, and we will learn these skills by using the OCaml language.